physics at the same time. Abdus Salam was a Nobel Prize-winning theoretical physicist, and he was the first Nobel Prize winner from Pakistan. He then played a key role in establishing Pakistan's scientific infrastructure, and he established several committees and physics research societies in Pakistan and abroad. His work on physics had several important breakthroughs. One of them, for which he won the Nobel Prize, was his work on the electroweak force, which is one of the 4 fundamental interactions in physics. For point of comparison, gravity is one of the other 4 fundamental forces. So it was a huge discovery, and he's been hugely influential in Pakistan and the rest of the world. To start today off, I'd like to introduce Iqbal Haider. He's the president of the Josh Society of Canada, and he's a poet, author, and philanthropist. And he'll be presenting the Eternal Quest.
Honorable guests, respected faculty members, ladies and gentlemen, on behalf of Josh Literary Society of Canada, I would like to welcome you all. It is truly a splendid occasion that a grand institute like University of Calgary has once again joined hands with a local society to celebrate the life and work of a supremely outstanding human being, Dr. Abdus Salam. The multi-layered effort is certainly commendable and has many facets to it. First of all, I must thank the faculty members, specifically Dr. Naveed Syed, to help us realize this long-awaited dream. This whole program has been designed and put together by his staff. We owe them big time. Please give them a big hand too. As we all know, we are gathered here today to pay homage to one of the greatest scientists of our time, a genuine intellect, a visionary, and above all, an extraordinary human being, the Nobel laureate, Dr. Abdus Salam of Pakistan. I must admit that as a poet and as a writer, physicality and physique are often my topics or points of interest, but physics is definitely not. But even if it were, I would dare not say a word in this august company. However, I would like to take a few moments to share with you a few lines from my article on Professor Abdus Salam, Rationality, Knowledge, and Faith, the Eternal Quest. I won't take very long. Dr. Salam was not merely a scientist. He was truly a symbol of dignified resistance in the backdrop of his social surroundings. He defied in his trademark, honorable way and never retaliated. He definitely seemed to have nerves of steel and a heart of gold. He was ignored and mistreated by some ill-advised and short-sighted politicians, mullahs, and bureaucrats. But that did not sway him from his path of humanism. All his life, he kept helping and promoting the very same people who discriminated against him. I do not want to go to all the details, but we all know what he did for Pakistan, and it was all very substantive. He is our biggest yet least celebrated national hero. It's a shame, but that's the way it has been so far. He remained steadfast in his belief, generous in his actions, compassionate in his wisdom, and patriotic in his thoughts throughout his life. He lived and died as a principled and proud man. Yes, at times I feel ashamed, I think we all feel ashamed, at the treatment he was meted out by some. But then again, I also know that almost all his countrymen do love him and hold him in the highest regards. We know that present is often harsh to people who belongs to the future. It takes time to accept changes. It takes time to accept change, sometimes a lifetime. He was truly an enigmatic human being, hence a genius. Salam's legacy continues whether we talk about Higgs boson, which is popularly dubbed as God's particle in present-day context, or the grand unified theory or Salam model. Somehow or the other, we feel in the heart of our hearts that we are getting closer to that elusive eternal quest. It is also interesting to see that Professor Salam was astonishingly different in his belief system from his fellow scientists, especially his most eminent contemporaries. Why it is so intriguing? Because it goes to show that pursuit of knowledge, scientific research, rational thinking, and objectivity of cause and effect do not matter when it comes to one's belief, or non-belief for that matter. In fact, we really think about it, if we really think about it, non-belief is also a belief. Incidentally, the three scientists who jointly shared the Nobel in 1979 for their independent work on unification of electromagnetic and weak nuclear forces had distinctively different belief systems. When it comes to their attitude towards religion, deity, or faith, we find Dr. Abdus Salam and Dr. Steve Weinberg in opposite camps, whereas Sheldon Glashow was somewhere in the middle. If one was a conformist, the other was a nonconformist, and the third being somewhat noncommittal. Yet they redefined the mass structure of particle forever. Dr. Salam attributed this grand unified force to the unity of God and quoted many heavenly references, whereas Dr. Steve Weinberg saw no such liaison. This phenomenon is not only typical of science, but is evident in almost every faculty of knowledge. Maybe the rise towards the peak takes away the lateral distance, and perhaps that's where the distance lies between belief and non-belief. In the history of mankind, there are a great many people, thinkers, visionaries, poets, and sages who acquired knowledge through a totally different source or discipline, but came to a similar situation and faced even harsher consequences. The knowledge source towards oneness, that's where the top might be a lonely place. This society is named after, these excerpts are just from different part of the article, so they're not related to each other. This society is named after such a person, Josh, a visionary poet who not only yearned for the oneness of mankind, but also relentlessly and fearlessly pursued that eternal truth. He was a well-known nonconformist and notoriously blunt about his beliefs. In 1975, when asked by an interviewer, excuse me, if he believed in God, he swiftly replied, he did not believe in the personified and man-made God, but do think that there might be a grand energy or a force behind this universe. Yet, it is not known whether it is conscious and discernible or not. We enjoy this similarity and the diversity of knowledge, hence the necessity to celebrate Dr. Salam from the platform of this literary society. In the end, please allow me to conclude with one famous couplet of Josh, which is a tribute to the universal man, but fits Salam like a diamond to a ring. I would try to summarize. I cannot translate it. I don't think anybody can, but I will, because of the diction, but I would just summarize it and then read the couplet. The universe is like a massive knot and the man a fingernail. The God's command will go hollow if not for the man. And in Urdu, the share is like this. Uqda kul afaq naqun admi. Uqda kul afaq naqun admi. Abruwe naghmae kun admi. Thank you.
Thank you, Yopal Haider. Next, I would like to invite Dr. Barry Sanders, a professor here in the Department of Physics and Astronomy at the University of Calgary. He's the director of the Institute for Quantum Science and Technology here at the University of Calgary, and he also holds a Chien Ren B Chair in the Division of Quantum Physics and Quantum Information at the National Laboratory for Physical Sciences at the microscale at the University of Science and Technology, China, and he's an adjunct professor at the Raman Research Institute. He's also the recipient of several prestigious awards and grants. Dr. Barry Sanders.
I'd like to first thank the organizers for the privilege of speaking. I did my graduate work in the department that Professor Salam was in, so I knew him just as a very junior student, and like all the other students, when Professor Salam would come in, we were just in awe. We all, stayed quiet. We were impressed, and the idea that 30 years later, I'd be standing up giving a tribute to him is a great privilege. So, I never thought I'd be in this position. So I'm very happy to be here and talk about this. I titled the talk Abdus Salam, the Grand Unifier, and I did it for two reasons. So I want to tell you two sides. I want to tell you a little bit about the physics he was doing, which was characterized by seeing a grand unity in nature itself, and I'll elaborate on that. And then I want to finish by the other work he did, that he saw science as a great gift to humanity, and he felt that science was heavily concentrated in only a certain part of the world. So he did an enormous amount of work to encourage the developing world, and especially Pakistan, to develop its own science. And I remember thinking back then, so back in the days when I was a graduate student, Professor Salam wasn't around that often. Whenever I had to take people on tours, I would show them his door. His door was almost always closed. He wasn't there. And I would stand at the door and explain what he was doing when we had visitors around. But he was often at Trieste in Italy, where he, during the time I was at Imperial College, he was off in Italy a lot of the time, putting a lot of his energy into founding the International Center for Theoretical Physics. I'll tell you a bit more what Professor Salam and I have in common, but ultimately it comes down to the atom. So up here you see the standard rendition of the atom. Electrons going around. Inside there's a nucleus. Inside the nucleus there are particles, protons and neutrons. And then inside those particles are other particles. And then we think we hit the bottom, although it's possible there are other particles, sometimes called prions or rishons, that lie inside. What was at the bottom of the bottom of the bottom was really where Professor Salam dedicated his thinking. So that was really the question. What's inside the nucleus? What are things made of? Of course, underlying all this is quantum mechanics. And I'm just going to explain all of quantum mechanics to you in 1 minute with this one slide. And so the idea in nature is that normal in life, we think of everything as being either fields or particles. And fields is like the light. You turn on a light. Light comes in some sort of a wave. There's water waves. Gravitation comes as waves. Nuclear forces behave like waves. And then there's particles like atoms, the electrons inside the atom, molecules. These are particles. And quantum mechanics recognizes that they're both really the same thing. So this picture by Douglas Hofstadter, whose father was a Nobel laureate in physics, as well as Professor Salam, just did that picture a number of years ago to try to get it. So it says light is a, and then you decide what it says next. But that was, one of Douglas Hofstadter's expertise is linguistics, and so he used that to convey the idea. By the way, any Big Bang Theory fans here might recognize the name Hofstadter. So the Hofstadter on Big Bang Theory is an eponym commemorating Douglas Hofstadter's father. Okay, so I just thought I'd put up an academic tree. So we all have families, and we think about parents and children and siblings. And there's, so in the academic world, we think about it. So I just wanted to put up my connection through to Professor Salam. So there's me at the very bottom. And then on the left is Tom Kibble, who was my master's supervisor. He was one of the Higgs boson discoverers, but missed the list for the Nobel Prize when it came out. Above him is Polkinghorne, who was very interesting, physics, and then he became a Christian minister, Christian theologian at some point. And then above him was Professor Salam. And we heard about how Professor Salam was extremely open in his belief system, and I'll tell you a bit more in a moment, but he was very happy to entertain discussions about science, about religion, and always open and clear in his discussions. So there's Professor Salam, and then above him is Nicholas Kammer, who was born in St. Petersburg, and he was a German, ethnically living in Estonia, and things got complicated in Europe. He went off to Britain, and he wound up being Professor Salam's supervisor, and he's famous for something in particular. Oh, this is just a blow-up of it. You can see that. Actually, it's very intimidating when I looked at this academic tree, because I just do what I do. And just like there's half a dozen Nobel Prize winners in the list. And there's nothing like realizing that there's a lineage where you'll never reach. It's kind of intimidating there. Anyway, so that was it. And then I just thought I'd mention that Professor Salam's supervisor, Kammer, is the one who named neptunium and plutonium. So if you know about those unfortunately nuclear weapons, nuclear power, that kind of thing, it was Professor Salam's supervisor who invented the names. Interestingly enough, when Professor Salam arrived to do his studies, he was actually, Professor Kammer didn't have a problem for him yet, so he just told Professor Salam to spend some time with Paul Matthews, who also went to Imperial College. And Professor Matthews, just kind of as a joke before he went on holiday, said Professor Salam wanted to know what to do, and Professor Matthews then said, why don't you solve the problem of renormalization in quantum electrodynamics? And the problem there is that the theory has these infinities. It turns out that when you try to solve things and you get to the very, very tiny scale, your mathematical expressions blow up. And it stumped top people at the time. You might know about Richard Feynman, Freeman Dyson. Various people were all stuck on it. So as a joke, Professor Salam was given that as something to work on. Sure enough, when Professor Matthews came back from his holiday, when they were both students, Professor Salam had solved the problem. So as an early stage graduate student, he solved a problem that stymied other people who would win Nobel Prizes, and then he was very famous. Everybody knew the name. So I was going to mention, this is my recollection, so just remember I was a very junior student, and Professor Salam didn't know me. I would be in a room when he was there and hear him talk and that kind of thing, but it was a one-way street. So I was doing my diploma of Imperial College in the department that he founded. So he founded the department around 1956. I was there in 84 to 85. The year I was there was actually very exciting. It was the birth of superstring theory. You might have heard of superstrings. So I had just started, and suddenly this whole wave of excitement, everybody quit what they were doing, do superstrings. And over here, I just remember a discussion, like a very exciting discussion, which broke out into just 3 people were left in the room. There was Professor Salam, his former student Yuval Ne'eman, and Chris Isham. This was one of these interesting religious mixes too, because they all had 3 very different belief systems. And they were sitting there. I was kind of fascinated because it was these 3 people who, on the face of it, have very divergent views, but they were just debating very heavily. And I just sat in a corner of the room. I was the 4th person, hoping they wouldn't notice me so I could stick around and listen. So that's what I remember. And I also remember at the time the stories of ICTP at Trieste, his founding of it, and I was thinking also about the idea of science in the developing world. Here's a picture of the department that he founded and the one that I did my master's degree in. So it's the Theoretical Physics Group in 1964. In the middle you can see Professor Salam. On his right is Professor Kibble. That was my supervisor. And then there's some other luminaries in there. And through Professor Salam's leadership, Imperial College rapidly rose up to be one of the top theoretical physics groups in all of Britain and probably in the world. And a lot of the Higgs boson work, Higgs was in Edinburgh, but a lot of structure for that came out of this group. So I'll just tell you the physics briefly to give you an idea. I mentioned before that what Professor Salam would think about was what's inside the atom. So over here you can see just a cartoon rendition of the atom and its size. Inside there's a nucleus. Inside the nucleus there are protons and neutrons. These are known as hadrons. There are other kinds of such particles. And inside those are quarks. And around the atom, you have the electron moving. And in the introduction, we heard about the Salam model. So one of the problems he worked on, which is still a viable alternative theory today in particle physics, is to try to unify the quark and the electron. So the idea is that he wanted to construct a theory that thought kind of like of the electron like a fourth quark. And if you have a unification frame of mind, it would bother you that there's quarks and leptons. Just like I said, waves and particles are unified, they should be unified. And so he worked on that particular problem and developed a fourth color of quarks, made a very nice theory. What he's most famous for, and there's actually a number of things he did, what he's most famous for is the electroweak unification, which is what he won his Nobel Prize for. So in this picture, what you see is a beta decay. And a beta decay, if high school labs look at alpha, beta, gamma type decay, and a beta decay fundamentally is that the neutron can turn into a proton, and when it does so, it gives off an electron and an antineutrino. And so the physics underpinning it, and actually the recognition that neutron and proton are two sides of the same coin, is part of the weak theory, and where Professor Salam and the others made the great contribution in this area was another unification. It was the recognition that the weak nuclear theory that was responsible for beta nuclear decay and electromagnetic theory that describes the light in the room are the same thing. So the idea that light is carried by photons, and then there's W and Z particles that carry the weak force, and they're two sides of the same coin. And in the very early universe, when it was really, really hot, they were the same force, again, was a fantastic unification. I'll mention one other. There was a Nobel Prize for what's called parity violation. So the question is, should the universe look the same if you looked in a kind of a mirror? And the answer should be yes, except in the weak theory, the answer is no. And Professor Salam figured it out first. He wrote a paper about it, but Wolfgang Pauli, so Professor Pauli, who did the Pauli exclusion principle and figured out electron spin, gave Professor Salam such a hard time in conferences and criticized it that even after the paper was accepted, it was ready to be published in the journal, Professor Salam contacted the journal and said, "Pull my paper, I'm no longer sure." And then Yang and Lee had their paper out a few weeks later in 1956 and got the Nobel Prize for it. So if Professor Salam hadn't pulled his paper, it's likely that the parity violation Nobel Prize would have gone to him as well. Okay, and here's the Pati-Salam concept. There you can see the hadron, proton or neutron, and in this case it's 2 up and 1 down quark. And in the background you can see all the lilacs. So the idea is that there are quarks that make up these particles. They come in 3 colors. He introduced another color that he called lilac. Later, less imaginative people renamed it violet. So it's known as violet, but I like the lilac color. And so that was the Pati-Salam grand unified theory, was to say that in some ways the electron is another kind of quark. And he did the mathematics for it, and it's really important. It's not just that he thought, hey, I got a really nice idea, doesn't it look pretty? He would actually do all the very hard mathematics and have to push the mathematics to the limit in order to make his theory consistent with other theories. When you unify theories, you have to take the mathematics from the different theories and construct one unified mathematical framework. So he was able to do that. Really fantastic. I thought I'd mention briefly how intellectually this filtered into my own research. And I don't want to talk a lot about what I do, but I'll just mention that one very important area to me is just sending particles of light into interferometers in very complicated ways. So here in the 21st century, the quantum theory 60 years ago when Professor Salam was working on this stuff was really, you have to look at atoms, nuclei, what did nature give you? Nowadays we have technology that we can make quantum mechanics on a grand scale. And so even things like how does light interfere with itself, nowadays there are interesting issues that arise using his kind of mathematics to study those kinds of problems. So intellectually, I feel like I'm a descendant in the sense that I still love using all that mathematics, but instead of studying what nature gives, I prefer now to study what we could create out of the bits of nature. So that won't explain the picture, but that's the idea. Thank you. Okay, now I wanted to switch gears and just talk a bit about his unification in terms of science and the world. I mentioned a bit about the International Center for Theoretical Physics, which I visited Natya Gali in Pakistan. So I was there. I was invited there again. So I think I've been to Pakistan 5 times now, and I never say no. I always enjoy going. And oh, sorry, that's the lower one, the International Natya Gali Summer College, lower down. That got closed 2009 after the Osama bin Laden attack because of the proximity. So the center is not that far from Abbottabad, which is where that happened. So now those meetings have been moved to Islamabad, unfortunately for me, because I really like Natya Gali, and I don't know if anybody's been there. Miranjani is the mountain, and very, very nice place to go around. So he founded the International Natya Gali Summer College in Pakistan. He was also a science advisor and many other things. But he really wanted to found ways to see a connection between the local communities and the international scientists. And above, the International Center for Theoretical Physics gets money from a lot of places around the world and funds scientists from the developing world in order to take their science to new levels. And he had a particular interest in the Islamic world. So he was so I talked to a friend of mine who was a student at the same time and knew Professor Salam better. But he was a great reader of the book by George Sarton, History of Science, which had each half century would list the leading scientists of the time, and then he would talk. He'd go around in London and talk at a mosque in London and talk about how you look at the early history and everyone, almost all were Muslim, there were a few Jewish ones on the list, and then it all disappears. So he was kind of passionate about getting that buildup of activity. So he founded these, and he did a lot of other activities I don't mention, but he really wanted to give back to the community and create stuff. So I thought I would just mention that, in my own little way, I'm trying to follow that example. This is my trip advisor, so I travel too much, I think. But you'll see in here, there's some various countries that are interesting. And I thought I'd just put up some pictures to show what goes on nowadays, partly funded by what he founded, and I have my own role. Up on the upper left, I'm not showing you tourist-type photos of the scenery. I'm just showing you what we scientists do, which is usually sit in desks or have coffee and talk to each other or something like that. That's actually in Natya Gali, that picture there. I'm the one on the lower right looking away. And it's just all of us sitting there in the evening. It was hosted by the Atomic Energy Commission of Pakistan. The leader of that came to the event, and we were sitting there. There was a musical event. But that was the Natya Gali Summer College on a hill station, Pakistan, that we were. And then since then, I got kind of inspired by that, and I've been organizing various meetings. I do a regular meeting in Iran that you can see in the lower right. I have that involvement in India and various others. Brazil, I've had some involvement with helping them out. More recently, I've been working on a series which is called Quantum Africa, where we do the same sort of thing. I got a lot of money, support from International Center for Theoretical Physics. That was a meeting in Rabat last September. Next year it'll be in Tunisia. I've been helping with meetings in Egypt, Algeria, etc. So not helping Algeria there, I was invited to speak. But you get the idea, like this whole internationalization's happening, and it's almost impossible to consider getting a meeting going in countries that are traditionally underdeveloped in science without thinking of Professor Salam and the funds he established. These things would not be possible. Those funds are quite important. In fact, I've been advocating this. This is an article I wrote a number of years ago, Science Without Borders, where I've been advocating that in the same spirit that we should be conducting science regardless of nationality, religion, politics, all that stuff. So I had an article on Science Without Borders. Sure enough, I just thought I'd show you. There was a letters back. This is the Science Not Yet Without Borders, where a lot of people actually hate the idea. They see science as very political. And so I thought I'd mention that. But there's me and a few others who really feel that Professor Salam's vision was worth keeping. So I'm just ending the second half of my talk by telling you, that in the sense of Professor Salam and the attempt to unify people who are interested in science, regardless of nationality, religion, political persuasion, everything, we have other organizations like Doctors Without Borders, Teachers Without Borders that do that. I put up a logo. There is a Science Without Borders, but it's very different from what I'm talking about. So I think of Professor Salam as kind of the founder, in a conceptual way, of an eventual Science Without Borders that would make the world a better place for that purpose. And so Professor Salam influenced me greatly in the science, But I just wanted to add that his influence in the way that he thought and spoke about bringing science to humanity, I think is a much bigger impact on me. And I always think about him and his example. And again, it's really a great privilege to be able to stand here and tell you what a great influence he was on me. Thank you.
I would like to next introduce Dr. Rashid Uyed. He's also a professor in the Department of Physics and Astronomy here at the University of Calgary. And he received his PhD in astrophysics, and he's a member of the Canadian Astronomical Society, among many other societies. He has published over 120 papers in the field of astrophysics and has published in prestigious journals such as Nature. He is a recipient of many prestigious grants and holds several competitive grants from national granting agencies.
Privilege to stand here and talk about Abdus Salam. What I would like to do, though, I'm going to try to, for me, he's a superhuman. He's an impressive individual. So I would like to take you inside his brain as a physicist. Okay? So I'm going to try to basically bring his physics to the layman's level, and hopefully you'll see his contribution to physics and astrophysics. Right? These are, so originally I wanted to use a different title, which is Up the Tree and Down the Five Rivers, like that, right? Because I read a few books about his life as a human being as well, but the more I knew about his science and physics, the more I appreciated his power as a human being. So that's the tree and the five rivers I'm going to follow, those that are inside his brain. Okay? This is when he received this prize. The reason I like to show this, if you want to steal the show, just have a turban and gold kusa like this. And I like this one in particular. So if I win something like this, I don't have to say anything afterwards. Right? But he did much more. He spoke much more and helped much more. Okay? So if you look at these 4 points, which are the points that usually people refer to when they discuss him as a physicist, there are 4 highlighted texts in here. The Higgs mechanism is part of his contribution. He predicted the unification of 2 fundamental forces, the prediction of the weak neutral current, and again, the Higgs field is in there. Right? So his contributions go much beyond just the unification of the electroweak force in here. But before I get you to understand why he won the Nobel Prize, I'll just going to take you step by step in how he got there, how he thought about nature, how he thought about particles and forces, and how his unique view led him to actually not just change physics, but actually change astrophysics as well. So we start with elementary particles. And these are quarks that Barry mentioned. And these are leptons, including electrons and neutrinos. Every block of matter we know are made of these particles. Okay? In fact, if you look at all the matter around us, if you look inside the proton and neutron, they're made of quarks. Up quark, down quark in here, which are these 2 guys. And to create atoms, you just combine protons and neutrons and put electrons around them, and that's how you create atoms. Okay? So these are fundamental blocks of matter, of us. Okay? And once you do that, you can make all the way, your way up from the quark to proton, to nucleus, to an atom, to molecule here, to a virus in here. But he has always been dealing with these unknowns in here. Okay? So those are the particles in here. But his main interest really was these guys here. These guys are the force mediators. You see the photon here, the gluon, the Z and W, which he won the Nobel Prize for. These guys are the ones who allow the building block of matters to talk to each other. And this is where his interest was. That's what his contribution was. So in a sense, you can think of those as the spices that you can use in order to combine these leptons and quarks and create matter. Okay? Those are the spices that gives the flavors and gives the matter its strength and its force. So just keep in mind the photon and the gluon here. So the electromagnetic force is mediated by the photon. So this is a Feynman diagram. We cannot give a physics talk without having a Feynman diagram. So what this is an electron exchanging a photon with another lepton. And then the electron keeps going on its way. This guy gets the photon and keeps one its way. So what I'm doing in here, so if I throw the ball here, send up. So we exchange the photon, basically. And I'm giving him some information. This is a mediator of the electromagnetic force. And this is a photon. And the photon has no mass. It's a zero mass. Okay? That's one of the forces. I can interact with anyone by throwing the ball. And you open the ball, it has information. You follow the information. We exchanged electromagnetic information here. The strong force, it's the same thing. It's two quarks talking to each other. And they exchange what's called the gluon. Okay? So the gluon is the mediator of the force in the case of the strong force. So that's two forces that we know of. And then comes the weak force. And the weak force is a bit bizarre. This is the one that Salam had to deal with. It's not similar to the photon and the gluon. It's really unique in a sense. So that's the first challenge you had to face. So if you look at radioactivity in here, you take carbon-14, it decays into nitrogen-14, and it releases an anti-neutrino and an electron. Okay? These are the other particles that I've shown early on. So we have the quarks and the electrons, but these neutrinos here and their anti-neutrinos, they do not contribute to matter. They do not play any role in building matter. So if you take an atom, you have quarks and electrons, that's it. Neutrinos do not contribute at all. So it's very strange that a carbon-14 turned into nitrogen-14 and creates an electron antineutrino. And we know this electron is not one of the electrons of the carbon-14. We know it's something that came out of the blue. Okay? But then what happens, one of the neutrons inside carbon-14 turns into a proton. And this is how you form nitrogen-14. And this is radioactivity. So it's a very different kind of interaction. It's like if I throw the ball, instead of him standing up, he becomes a dinosaur, and then a goat, and that comes out, right? So it changes the flavor, the nature of particles. So it's quite different. And it's not a force like we know. It's not like electromagnetic force. It's like a friction. Force of friction is not a force per se. There's an underlying fundamental force in it. So this weak force in here, it's basically a neutron inside the carbon-14, slowly peels off, and then turns into a proton. And at the same time, as it peels off, it ejects these exotic particles, in particular the neutrino here, like that. And this is how the Feynman diagram looks like. Okay? So the neutron becomes a proton in exchange this particle, which Abdus Salam is famous for, and it gives you the electron and neutrino. So he was really related to one of the most bizarre, most strange forces we know of, which is the weak forces. But it bothered him a lot because, so these are the particles in here, but I don't want you to focus on the left side. I want you to focus on the blue box here. There's the gluons that mediates the strong force, like the quarks. This is the photons that mediates the electromagnetism. This is the gravitons, which mediates the gravity. And the weak force is in here. This is a bizarre force Abdus Salam had to deal with, right? It's a very force to deal with to start with. So Maxwell unified magnetic fields, an electric field, created electromagnetic force, which Feynman quantified later. Okay? And what Abdus Salam was thinking, oh, why can't I unify the weak and the electromagnetic force in here and create a unified force? Okay. And this is his grand challenge. It was a very hard problem back then because the weak force was very different from the electromagnetic force. Okay. So this is the diagram basically he was thinking about. We live down here. As you go to the left, you go back in time when the universe was hotter and the energies are higher. And he was saying, maybe the electromagnetic and the weak force unified at some point here. Okay? And they become the electroweak force. And later down the road, when the temperatures and energies are high, back in the earlier stages of the universe, the strong and the magnetic electroweak force will unify to give the grand unified theory here. And then maybe gravity will unify with this grand unified theory and give the theory of everything. So in physics, there is such thing as theory of everything. Okay? And he spent every second of his life down this road here. He just could not sleep. He had to understand what was going on. He was born with it. Okay? That's what he says. He said these two spices probably merge in here before they unify. So he said, okay, what if in the early universe, this is the analogy I like to use. This is, it's called the phase diagram of water. This is the pressure and temperature. If we live around this line here between ice and water, then ice and water coexist. Okay? So if you live at 0 degrees Celsius, ice and water will coexist. But if you increase the temperature, guess what's going to happen to the ice? It melts and you only have water, right? And he's thinking, wait, maybe the electromagnetic force and the weak force used to be the same thing as you go to higher temperature. And as the universe cools, something happens and they broke down. Okay? It's a marvelous idea. That's what created everything we know about particle physics. Right? And that's what he did. He said, what if early on we just have 4 things that all like photons, right? Like 4 balls like this, and they just roam around, they have no mass, and something happens, and the 3 of them got mass while the photon escaped. So basically, he came up with the idea of the Higgs field, him and Weinberg and others. They included the Higgs field, which is the big news in physics lately. It was part of the theory that he developed. By bringing the Higgs field in here, which is another particle that's roaming all over the universe, he was able to show, him and Glashow and Weinberg, they were able to show that out of massless particle, you get a photon, and the 3 mediators of the weak force, those who behave very strong, those who give you radioactivity. Okay. So to do so, he said something must have happened, that symmetry had to be broken. So imagine you have a bar like this, okay, and you push on the bar. You push really, really hard, and you keep increasing the force, and you keep increasing it as hard as you can. Eventually, it will give away, right? If there's a lot of perturbation, it could bend this way, it could bend, let's say, this way, or towards you, or the other way. So you have this 360 degrees way of bending, right? That symmetry allows you to create new particles. So you can take one particle and create subparticles out of it. Okay? And this is where symmetry comes into his model as well. So imagine, and another analogy that I like to use, if you're sitting here at the top, a little bit of perturbation will roll you down in more stable position here. But you can roll down any way. You can roll down this way, that way, 360 degrees. That behavior allows you to create these particles that are massless. But by introducing the Higgs field, which is a field that's everywhere in the universe, he was able to show that you can create these mediators of the weak force. So he was able to unify them. You get 4 particles that are massless, and then something happens as the universe cools, and the Higgs comes in, and 3 of them becomes the mediator of the weak force, and the other one is the photon. And the reason the photon remains massless, or has no mass, is because it just happens that the photons were swimming in the same direction as the Higgs field. You can think of the Higgs field as a river that suddenly flooded your area. Okay? If you go along the river, you just remain massless. You don't feel its effect. But if you try to swim up the river, you feel the force of that river, and then you gain mass. Okay? That's the simplest way I can take his work and bring it to this level of understanding, because there's a lot of complicated physics and math in there. So he allowed us to have charts like these. before, we could not understand what these guys were. Okay? So W minus, W plus, and Z here. So another thing he predicted is this Z0, which is a natural current. I'm not going to go into the details, which is an incredible prediction. And that's basically why they won the Nobel Prize. Right? So it's said in the Nobel Prize documents, arguably one of the most important theoretical achievements of the 20th century. They predicted the W and Z particles, among other things. And they have fundamental connection to the Higgs field. Okay? Higgs field was actually part of their research. The Higgs field was hypothesized before, but until these guys used it, it didn't have the value it has now. The fact that it made use of Higgs made Higgs actually more important than it used to be. Okay? As a physicist, you know, it's fascinating to read some of his work. It's fascinating to know there are physicists like him who think like that. I always wonder where he got that idea from, you know? It's just bothered me. Where did he get the ideas from? How can he think of unification? These are the 5 rivers. Okay. And as Barry said, mirror symmetry is an important thing of his research, right? So if you take the mirror symmetry of this unification diagram, okay, we can find strong connection, amazing connections to the 5 rivers in here. Okay? Yeah. I always been fascinated by this connection. And I had to do the mirror symmetry in order to find that connection. And then mirror symmetry is a fundamental property of electric theory. So if I add here, I added the electromagnetic theory of Maxwell. It's hidden. There is a bifurcation in here. So if this is true, it means that the 5 rivers are predicting that somewhere down the road, the strong force is going to split into 2 halves, right? So maybe it's an avenue for research, too, right? It's fascinating, isn't it? So that's more or less the downriver kind of connection. So the Higgs field is something that had to be discovered because they had to put it in their models. They had to put that in the theory. So although he got the Nobel Prize for unifying the forces, we still needed to find the Higgs field. So what the Higgs field does, it gives a mass to one of the particles that Salam and Weinberg and Glashow discovered, right? So we needed to make sure it existed, right? These are Nobel Prize for the Higgs field, which happens much later after Salam. So what happens is that you smash particles at CERN and Large Hadronic Collider, and you need to smash millions and billions of atoms. So you smash them, and hopefully one of them will give you a Higgs particle. Okay? So you take one, you smash it, you look nothing. You take another one, you smash it, you look nothing. And you have to do, for years and years, you have to do millions of experiments every day for years in order to be able to find, hopefully, one event. So that's why it took a long time, many efforts. And eventually, they found it. See this little bump in here? That's what they were looking for years and years. So you had to have a huge amount of events and data in order to find the Higgs field. And once it was found, so basically, not only confirms Salam's and Weinberg and Glashow's work, but also allowed people like Higgs to win the Nobel Prize as well. Okay. So other contributions are numerous. He has contribution in physics and astrophysics and general relativity. His paper is always the same, very strong mathematical background, very well written. This is the one Barry mentioned, I think. But most of these papers has supersymmetry, supergravity, superunification. Everything he did was super, right? Because he was superhuman, right? And it was really enjoyable to, as a physicist, you know, to have been exposed to his work early on, because it gets better with him. The more you read about him, the more you read about his papers, the more you know about how he wrote the paper, the more you know about his connection to other fields of science, you appreciate the man even more, right? But the best way to appreciate him really is to go into his physics. This is what I try to do, is really try to get you down the 5 rivers of physics in order to appreciate more the person. But on a personal note, I think it's really something that's important. It's also a taste of the golden age of Islam. Like people like Salam, don't exist anymore. In the golden age of Islam, scientists were like him. They would travel a lot. They would collaborate with people from different faiths, from the Jews, the Hindus, the Christians. That's what they did. And in a sense, he's an ambassador of that time. It's another thing I appreciated a lot about him. So is that he unified things in many ways, not just in the brain and the mind and physics, but also in some beliefs. I'd like to stop here. Thank you. And you can find, I use quarks and neutrons and neutrinos and leptons in my research. And if you want to find more about me and my group, you can find us at the quarknova.ca.